Hey everyone, today we're working through problem 10 from Euclid 2022. So this question says, at Pizza by Alex, toppings are put on circular pizzas in a random way. Every topping is placed randomly on chosen semicircles, and each topping semicircle is chosen independently. So in this example here, the topping T1 is chosen on this top semicircle in yellow. Topping T2 is on this green semicircle, and topping T3 is on this orange semicircle. So Alex starts by drawing a diameter whose angle to the horizontal is selected uniformly at random. This divides the pizza into two semicircles. One of the two halves is then chosen at random to be covered by the topping, like we showed. So part A asks for a two-topping pizza. There's only two diameters and two toppings. Determine the probability that at least a quarter of the pizza is covered by both toppings. So to solve this part A here, let's draw a diagram. Let's suppose the first topping is going to be on this bottom side of the pizza below the horizontal. So no matter which way the pizza is arranged or cut, we can always just rotate the pizza so that the first topping is below the horizontal. So we're going to have another slice, another diameter, for example, something like this. It's going to intersect the first cut at the center of the circle, and it's going to have an angle theta. So once we have this second topping, the second topping could be either on the side that is away from theta, or it could be on the side that is with theta, for example, the orange side. And the chance that topping 2 is yellow or orange is 50-50 by symmetry because they are all different arrangements and they're chosen at random. So the angle theta here, let's define that. Theta could be between 0 degrees and 180 degrees. Notice that I'm saying theta is strictly greater than 0 degrees and strictly smaller than 180 degrees because theta is a continuous random variable. Continuous random variable. So there's exactly zero probability that theta lands exactly at 0 degrees or exactly at 180 degrees. So to determine the probability that at least a quarter of the pizza is covered by both toppings, we can look at the diagram here. So in this case, yellow does not cover a quarter of the pizza with both toppings, but orange does cover a quarter of the pizza with both toppings. So the key observation here is that no matter what theta is, there's always one configuration such that at least one quarter of the pizza is covered by both toppings and one configuration where it isn't. So for example, if theta is an obtuse angle, something like 120 degrees, and we chose the yellow side, so the side away from theta, this covers at least a quarter of the pizza with both toppings. But if we chose the orange side, the side with theta, then less than a quarter is covered by both toppings. So we can see that no matter what theta is, it's a 50-50 whether the side with an obtuse angle or the larger side will be covered by both toppings. So it's a 50-50 whether at least a quarter of the pizza is covered by both toppings. So the answer for question part A is 1/2. So for a 3-topping pizza, determine the probability that some region of the pizza with non-zero area is covered by all 3 toppings. So here, let's draw another diagram. So when we have 3 cuts of the pizza, that's going to divide the pizza into 6 different slices. Again, because thetas are continuous random variables, they're exactly 0 probability they land exactly on the same line. That means when there's 3 toppings, there's always going to be 6 slices of pizza. So let's call these toppings T1, T2, and T3, and just color them just so it's clear. So T1 is this yellow topping, and we chose it with a 50% chance to be on this side. Let me just color this. So T2 is the green topping, And also with 50% chance, it's on this bottom side. Same thing with T3, it's going to be the orange topping. So in this diagram, if it's chosen like yellow, green, and orange, we can see that there's exactly this one slice here, which is covered by all three toppings. So let's just draw a chart here for T1, T2, and T3. So, and also let's assign them variables. For example, when T1 is 1, that means we chose this yellow semicircle to be T1. If T1 is, however, 0, then we chose the opposite of it. So this unfilled semicircle to be T1, to be covered by topping 1. So, for example, if T1, T2, and T3 are all 1, that means it's exactly colored as shown, and this shaded slice is going to be filled with all three toppings. So, is there a region of the pizza with non-zero area covered by all three toppings? There is, so this is true. However, let's say T1 and T2 are as colored and T3 is the opposite. So we're going to reflect T3 over. Is there any part of the pizza that's covered by all three toppings? There is. T3 is reflected over. So this slice here, is going to be covered by all three toppings. So this is true as well. What about if T1 is true, T2 is 0, and T3 is 1? That means T2, the green semicircle, is reflected over. So in this case, we can see that there is no section of the pizza that's covered by all three toppings. So this is false. We can continue enumerating all the different possibilities here. 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0. There's going to be 8 different configurations because T1, T2, T3 can both be 0 or 1, so it's 2 to the power of 3, which is equal to 8. So in the next case, T2 and T3 are both reflected over. T2, so T3 is reflected over, and T2 is also reflected over. So we can see that this slice here is going to be filled with all three toppings. This is again true. So what if T1 is reflected over and T1 only? So T1 is the yellow slice. That means the slice down here is going to be filled with all three toppings. So this is true. If T1 and T3 are reflected over, if this is the case, we can see that actually none of the sections of the pizza are covered by all three toppings, so this is false. If T1 and T2 are reflected over, however, so this is T1 reflected over and T2 reflected over, we can see that this section of the pizza is covered by all three toppings. So this is again true. And if T1, T2, and T3 are all reflected over, then this previously white section of the pizza is going to be covered by all three toppings. So this is again true. There's 6 different configurations where we have at least one slice of the pizza covered by all three toppings, and each of these have equal probability by symmetry, because all the thetas are chosen at random, and there are 8 different configurations for T1, T2, and T3. So this gives us our answer here. There's a 3/4 chance that at least one section of the pizza, one slice, is going to be covered by all three toppings. So for part C, we want to generalize the answer from part B. So suppose there's an n is a positive integer for an n-topping pizza. Determine the probability in terms of n that some region of the pizza with non-zero area is covered by all n toppings. So for part C, first we have to notice how many slices are there if we have n toppings. So in part B, we noticed that with 3 toppings, there's going to be 6 slices because every topping requires the pizza to be cut in half along the diameter. So there's going to be 2 n different slices. So how many configurations are there for all the pizzas? There's going to be 2 to the n configurations. And we notice that from part B, every single slice has exactly 1 configuration where it is covered by all 3 toppings. For example, in this top slice here, this requires T1 to be 1, T2 to be 0, and T3 to be 0. So it's the 1, 0, 0 slice. If T1, T2, T3 are exactly 1, 0, 0, then this slice is covered by all 3 toppings. So the next slice here is it's already covered by T1 and T2, so it's going to be 1, 1, and we need T3 to be flipped over, so 1, 1, 0. So we can see that for every slice, there's exactly 1 configuration of T1, T2, and T3, or the different toppings, such that it's covered by all of the toppings. So going back to question 3, part C here, there's 2 n different slices. Each slice has exactly 1 configuration where it's covered by all n toppings. And there are in total 2 to the n different configurations because each slice can be either 0 or 1, for example, on the left side or on the right side of the line. So simplifying this equation by 2, we are going to get n over 2 to the n minus 1. And that is the answer for part C. The probability that for an n topping pizza, at least 1 slice of the pizza is covered by all n toppings. And that's it for question 10 of the 2022 Euclid. Thank you guys for watching, and credit to Ethan for this brilliant solution.